wanted to do here was just a couple more assembly examples, since I kind of did a little bit quickly in class. Now, granted, in graduate classes, we tend to do a little more emphasis on assembly because the students actually implement this a bit more, in a programming language. And I kind of gloss over quickly here, but let me just do a couple more examples. It'll help do the assignment as well, or help gratification in general. So here's a real simple model: 2 elements, 3 nodes, and we showed in class how you can get this by considering sum of forces at each node. So for example, this would be the second node, and you have the tensile forces. This is the stress in element 2 times the cross-sectional area of element 2, and this is the stress in element 1 times cross-sectional area of element 1, and then we can have the external applied force F2 there. So you can get the 3 discrete finite element equations by doing sum of forces at each node. Now, this is something that's not so easy for computers to automate, so instead we have this sort of assembly process. And I showed how that works very quickly and visually, looking at the overlapping of the stiffness elements. But let me show you another approach that's maybe a little more rigorous and somewhere in between the two. And this is this notion of a augmented stiffness matrix. I wasn't going to cover this, but I noticed in the second homework I call it this. But this might help if you're still a little confused about how the scattering goes visually. Maybe this will help bridge that concept a little bit. So if you look at this system, we have 3 degrees of freedom for the whole system: U1, 2, and 3. So we know that each global stiffness matrix, that the global stiffness matrix is in fact going to be a 3 by 3. Right? And it gets multiplied by the nodal unknowns, U1, U2, and U3. Okay? And that's going to equal the external forces F1, F2, and F3. So if you think about it, each row corresponds to a sum of forces at node 1, sum of forces at node 2, and sum of forces at node 3, whereas the columns are associated with degrees, the actual global degrees of freedom, U1, U2, and U3, and that comes about because of the way we do a matrix vector multiplication, and you have the dot product of the row of the matrix with the column of the unknowns. So when I do the augmented stiffness matrix, what I do is I write the stiffness matrix for each element, but in the global stiffness matrix. So if you look at it this way, like I'm going to actually write this augmented stiffness matrix, but for element 1. And then I'm going to add on to it an augmented stiffness matrix for element 2. U1, U2, U3. It's also going to get multiplied by the nodal unknowns. Here's the 3 by 3. Okay. I'm going to discuss this approach a little bit. So it's called augmented because instead of you dealing with the 2 by 2 stiffness matrix, we augment it to be the same dimension as the global stiffness matrix. And again, so let's assume that there's a stiffness for the first element and a stiffness for the second element. So Ke is the area times Young's modulus over the length for that particular element. Okay? That's by definition, right? Okay, so the first element relates the forces at nodes 1 and 2 to the degrees of freedom at nodes 1 and 2. So it sits here. So in fact, you get the K1 minus K1 minus K1, and then K1 there, and you'd have 0 everywhere else. The second element relates the forces at nodes 2 and 3 to the displacements at node 2 and 3. So this gives me a K2 minus K2 minus K2, and then a K2 there, and again, zeros everywhere else. So if you think about this, this is the KD for the first element. So what we get here is really the force balance for the first element. Likewise, this is the force, the internal force of the second element. These are the forces that happen inside the system because of the stretching of the element in particular. These aren't the external applied forces, so these are actually internal forces of the elements. And if you look at this, we basically sum those together, and those have to equal the external force, okay? And in this case, that's the F1, F2, and F3. Now, obviously, you can pull the displacement vectors out. Move this over so you can see the whole thing. You can pull the displacement vectors out, and then what we're left with is, if I call this big K2, what I'm left with is big K1 plus big K2. These are the augmented stiffness matrix times the vector of the nodal unknowns has to equal the external force vector. Then if you just sum these two augmented stiffness matrices up, what you get is the global stiffness matrix, big K. And here you can see obviously that big K has to equal, just by adding these two together, K1 minus K1, 0, minus K1, K1 plus K2, minus K2, 0, minus K2, and then K2. Right? So it's kind of what we saw in class by just visually inspecting the overlap. It's the same as we got by that approach. Or if you were explicitly to write the sum of forces on the three nodes, you get the same set of equations. Okay? All right, so the nice thing about this is if you do something a little different, like, for example, we could do something like this. Most people would not write it this way, but again, the ordering and the numbering is arbitrary. So let's call this node 1, node 3, and node 2. And I'm going to call this element 1 and element 2. So what I've done here is I've swapped the names for nodes 3 and 2. In fact, obviously it's the same exact discretization. You get the same properties, but we've flipped the order. And actually, let me not do it that way. Let's call this, let's make it even more confusing. Let's call this 3. And we'll call this 1. We'll do it this way. So it's something different. Okay, so completely renumber the nodes. And again, you know, in general, we're going to have discretizations that are unstructured, and it's going to be real difficult to come up with some generalized consensus as to what is the correct node numbering. And, you know, it really isn't. It's kind of a silly statement. So the method should work for arbitrary numbering, and let's do it here. Okay, let's do this augmented approach. Again, you can do this by inspection if you see it, but if not, you might want to do this augmented approach. So let's write out the augmented matrix. Again, they're both going to be 3 by 3s. I'm just going to drop the displacement vector since you've seen that. I'm just going to directly sum them up. And this is going to give us, I should put a little more room on here. Let me zoom out just a tad bit. Okay, I think I can, well, we'll write the answer down here. So this is going to be the augmented stiffness matrix for the first element, the augmented stiffness matrix for the second element, and this is going to be the global stiffness matrix from the sum of those two. Again, they're both going to be 3 by 3s, so let's just sort of show the elements of the matrices. All right, so the first stiffness matrix connects the first element connects node 3 to node 1. So that's going to relate the forces at nodes 1 and 3 to the displacements at nodes 1 and 3. So where the zeros are going to populate are here, 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 and here. Now, technically, you know, if we look at just this is kind of a subtle thing. If I look at K11, K12, K21, K22, where this is the components of this element stiffness matrix for the first element, since the first degree of freedom is node 3, this one should technically go here. This one on the diagonal should technically go here. This one, which relates the first degree of freedom to the second degree of freedom, or the force at the first degree of freedom, which is 3, to the displacement at the second degree of freedom, which is 1. So that should go here. And then this one should go here. But you don't have to be that careful about the way those map because it's symmetric anyway, and you end up here with just K1 minus K1 minus K1 and then K1. Okay? This one works out pretty easily. Now the second one relates the displacements at, the displacements at nodes 1 and 2, this is like U1 and U2, to the forces at nodes 1 and 2. And in this case, the degrees of freedom, you know, the first entry would go here, so that's the K2, then we get the minus K2, minus K2, and then the K1. All right, and so if we write this out, we just sum those together, I get up here K1 plus K2, then I get a minus K2, and then I get a minus K1, and then I get a minus K2, and then a K1, and then a 0, and then a minus K1, a 0, and then a K1. And now if we compare those to the original stiffness matrix, let's see if I can get these right next to each other. Obviously, it has a different form, okay? But if you think about it, and I'll just mention this really quickly before I do the last example, this is really just a renumbering. So if I were to renumber this mesh so it would look like this, what would happen? And this one's a little confusing, because I would have to, let's renumber this. So in this case, what was originally 3 is going to go to 1. What was 1 in this mesh maps onto 2. And what is 2 here maps onto 3. Let me pause this. Someone's at my door. Oh, I can't pause. I wish I could pause. Let me stop.